Hello everyone, welcome to the second lecture in the series of lecture on semiconductor memories. In the first lecture, we have seen the idea of storing the data on silicon, various types of memories, and we have seen the memory array, the array in which the data can be stored and accessed in the memory. And the circuitry, like, we have seen a decoder circuit which is required to access a particular cell of the memory. In this lecture, we are going to talk about the read-only memory, that is ROM. Uh, in this lecture, the agenda of the lecture would be like first we'll see NOR RAM, NOR based ROMs, and in NOR based ROMs, we'll see various ways of fabrication of this NOR based memory. There is designs of NOR ROM. Then we'll see NAND based ROM and various fabrications. Of course, we'll see the stick diagram and the layout for both NOR ROM as well as NAND ROM. Then we'll see decoder circuit. In the decoder circuit, we'll see decoder for both row as well as column. These circuits. So that would be the agenda for this lecture. So let's start our discussion with the NOR based ROM. As we know, ROM is the type of memory in which we store data only once. And the type of ROM we are discussing here, which is programmed ROM, cannot be, sorry, it's a mask ROM. It cannot be programmed by the user. So the data is stored in the memory only once during the fabrication process. So NOR-based ROM, if you look at this truth table first, so here the truth table, we will see this structure of the circuit later, but first let's look at the truth table. So there are four rows, R1, R2, R3, R4. At these four rows, the data is stored 0, 1, 0, 1, 0, 0, 1, 0, 1, the second 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0. So this is nothing but the data. And here, this is output of row decoder. So this is output of row decoder, and there will be 2-bit address or 2-bit, let's say consider A1, A2 could be the address, and there are four rows R1, R2, R3, and R4, and at each row or at each location 4-bit data is stored. So at this point there is a cross point, there is one cell, there is another cell at this cross point, there is third cell over, there is fourth cell. So we are going to access 4-bit data. So the 4-bit data is stored at first location, another 4-bit data is stored at second location, and so on. Now we will see first how the data is stored in this array. As I have mentioned, this is a type of memory where data is stored only once, and that is during the fabrication. So we can look at it like a combinational circuit. So in the combinational circuit, so if I look at the combinational circuit, it has two inputs, A1 and A2, which is nothing but the address of the memory, and it has four outputs, C1 to C4. And for a particular value of this address, let's say 0, 0, it will give a set of values for the output. For another combination, it will give another set of output. So it can be seen as a combinational circuit. Having said that, as we know, a combinational circuit can be implemented using MOSFETs. That's why here the basic idea which comes to our mind when we look at the ROM is nothing but a simple combinational circuit. Now let's look at the circuit. Let's talk about the circuit now. So uh, this is called as NOR based ROM because if you look at these MOSFETs in one column, you can find they are connected in parallel. So uh, their drains are connected to the column line and their sources are connected to the ground, and there is a load device which is a PMOS. Okay, so in this these rows are called as word lines, whereas these columns are called as column line or bit line. So uh, see at this R1, you can see if I want to read R1, when R1 is activated, I should be able to read this entire data stored at R1 from C1, C2, C3, C4. That means when R1 is activated, I should get 0, 1, 0, 1. Okay. And because this all the MOSFETs in the same column are connected in parallel, like the NOR combination, that's what's called as a NOR based ROM. Now, how to draw this? Let's see first how to draw this, then we'll see the working. So the simple thing you have to remember while drawing it is wherever you want to have a 0, you just draw NMOS over there with the drain connected to bit line on the column and the source connected to the ground. And so this is nothing but a 0. And whenever you want to, wherever you want to store 1, you just don't connect anything. Just there won't be connection in row and column. Okay, so if there is 0, if you want to store, you should add active MOSFET over there, and when there you want to store 1, so there is no active transistor over there. That's a simple trick you have to remember. So if we say that, then suppose I want to store 0, 1, 0, 1 for C1, you can see because I want to store 0 over here, so it's 0. Here I have 1, there is 0 again, and there is 1. For line R2, you can see 0, 0, 1, 1. So it's 0, that means active transistor, 0, another transistor, then 1 and 1. Suppose that R3 I want to store 1, 0, 0, 1. So it's 1, that means absence of transistor, 0, that is presence of transistor, 0, another transistor, and 1, that is absence of transistor, and so on. Now let's look at the working. Okay, I hope you have understood how to draw this. I would suggest you to draw on your own because this question is frequently asked in exam to draw NOR based ROM and NOR based and NAND based ROM. So in exam they give you the data to be stored. Like they can ask you, you just draw a NOR structure to store this kind of data in the memory, and there's some data will be given. Then you have to draw a circuit based on this the content of the memory. So let's look at the working. Okay, so from the truth table you can see that whenever you want to whichever row you want to read, that row is made 1, that is it is pulled high to the logic 1, and the rest of the rows are pulled down to logic 0. So let's try to read R3, content of R3. So when R3 is 1, so if I want to read R3, so R3 will be activated by pulling it high. The rest of the rows will be pulled down to 0. So all the transistors which are connected on R1, because it's R1 is nothing but the gate of all the transistors. So this is off, this is off. Anyway, there is no connection over here, there is no connection over here. Similarly, R2, this is off, this is off, there is no connection, no connection. For R4, this is off, and of course there is no connection. Right now, the data which will come across C1, C2, C3, C4 depends upon R3, the row R3. Now, because 1 is connected here, this is on, this is also on. So, because this is on, so you can see there is, so if you look at this column, there is this connection over here, and this is on. So you can see a low resistance part to the ground. So even though the voltage at all these columns is 1, because your PMOS is all permanently connected to ground, so voltage at these points is always 1. Now because this NMOS is on, so it will find part to the ground, a low resistance part to the ground, so it is pulled down. So now here 0 will appear here. In case of this transistor, this bit line C3, here also you will find a path over here, and then small resistance path to the ground. So it is also pulled down. So that's why C2 is 0, C3 is 0. Now if I talk about the C1, now there is no transistor which is connected to ground, because this is off, this is off, this is off, and there is no connection here. So directly you will find C1, that is VDD, is connected to C1, so it is 1. Here also The only transistor that it had, C4, the only transistor it had is not connected to ground because it is off. So there is no pull down path for this point, and it is directly connected to VDD. So it's 1. So this is how a particular row can be read from this type of structure. So that's the working of NOR ROM, how the data can be read from it. Now, here there is one disadvantage of this kind of connection. The disadvantage is that there are several disadvantages or limitation of this. First disadvantage is its power consumption. It's and to be more precise, is static power consumption. So here you can see, even if you are not reading data or writing data, your PMOS is permanently connected to uh, ground. So they are always on. Because they are always on, so they conduct some current through them. So there is a conduction of current, which consumes some power, which is static power. Even if you are not reading from the memory or not writing to the memory, still there is a power consumption. So that's a static power consumption. That's one disadvantage. Second is, here you can see this is metal line. When you fabricate it, you will be fabricating it using metal line. This is gate, and there is a connection. Right? During the fabrication, you can see there is a metal to diffusion connection. So metal to diffusion connection takes some space. If you remember, it takes 3 lambda. The size of this connection is, or the buried uh, contact is 2 lambda, and then there should be specific distance between the 3 lambda should be distance between them. So because of this, the density is less as compared to, so it has less density as compared to NAND ROM. So these are a few disadvantages of this type of NOR based ROM. And then is a third disadvantage, I would say, because you can see all the transistors here are NMOS, and we have to fabricate PMOS, another layer of uh, mask, just to fabricate PMOS. So it adds to the complexity of the fabrication. So these are three limitations, I would say, in a NOR based ROM. One of the limitation can be overcome by using dynamic ROM. So the static power consumption can be reduced by periodically recharging these PMOSs. Instead of continuously charging them, we'll do it periodically. So we'll apply a simple clock cycle, and whenever it goes low, they will be pulled high. Otherwise, they will be off. So the static power consumption can be reduced by periodically recharging. The periodic recharge can be used. Then it will be termed as dynamic ROM. It is exactly similar to the static CMOS and dynamic CMOS. In static CMOS, PMOSs are connected to the input, and in dynamic PMOS, we periodically apply logic voltage, or so we periodically apply clock or voltage to the input of PMOS so that they are turned off for some time. So this is about the NOR based ROM. Now, even though the circuits are shown like here, now the density is the major issue. Can we work on the density of this? So one thing can be done. Now here, if you look at this row 2 and row 3, so row 2 and row 3, you can see it is one of the, its drain is connected to the bit line, its drain is connected to the bit line or a column line, and sources are connected to ground, sources are connected to ground. Here also at this point, you can particularly say drain is in R3, drain is connected to bit line or column line, and source is connected to ground. Now instead of having such kind of connection, the density can be increased by connecting this transistor upside down. So what would be the advantage of this such kind of connection is that they can share their source, because this source is connected to ground, this source is connected to ground, so they can share their source diffusion area. We'll see that in the next slide, but that will give you the idea. So to reduce the power consumption, what we have done is uh, we have used a dynamic load or dynamic ROM. Now, to increase the density, we can use some arrangement. So here you can see these are two rows which are shown over here, and the 4 locations over here. Now here you can see one transistor is connected over another transistor connected, third and fourth. So basically it is showing 2-bit data which can be read. And of course there are only 2 rows, so there will be 1-bit address. So it's a small portion of the memory. Okay. Now here you can see by fabricating it, we normally don't fabricate like this, because even if there is no connection, we don't uh, keep it as it is, or we rather what we do is we fabricate a transistor over here, but because we have to keep this open. So what we will do is we will avoid connecting drain to the bit line, or we'll avoid connecting source to the ground. Okay, so what we'll do, there will be a transistor. Of course, there will be a transistor like this, but we won't connect this to the bit line, or this is one option, or we won't connect source to the ground. What is the advantage of this type of? Why do we do that? The advantage is that then there will be uniformity in the mask, because everywhere you have to fabricate NMOS. So you will have one cell. So this is one NMOS cell, and which will be repeated over and over. So you will have a uniform cell, and then the only thing you have to do is you have to avoid the connection of drain to the bit line or source to the ground. So this is the practical way of fabricating it. So even though that's in circuit there is no connection, but actually there will be a transistor, active transistor, but its drain won't be connected to the bit line, or source won't be connected to the ground. Either way it can be done. So here you can see uh, in the R1, the first bit, you can see there is a dotted connection. That means there is no connection. The drain is there, but it's not connected to the bit line. So basically, it is absence of the transistor, right? So this absence of the transistor is nothing but 1. And here you can see in second bit, it's connected to the drain. So it's the presence of a transistor, it is 0. Now source of both are connected to the ground. So the source, you can see common, there's a common ground line, and it is connected to the ground. So there's a metal line which connects to the ground. Uh, Third, in the second row, you can see the third transistor over here. So you can see its drain is connected to the bottom. I mean, drain is connected to beat line, and the source is connected to ground, which is the upper one, upper terminal. So it's storing 0. Now the fourth transistor, second row, second bit or second column, you can see the drain is actually it is fabricated, but it is not connected. It is a dotted connection, whereas source is connected to ground, the upper terminal. So what we have done is, what is the difference between these two things is, here you can see all the drains are the upper terminal and the sources are the lower terminals for all the transistor. But in this case, for this R1, drains are the upper terminal and sources are the lower terminal. Whereas for R2, sources are the upper terminal and the drains are the lower terminal. So that actually we can say they are drawn upside down, R2, right? So basically it is storing 1 0 1 0 here, because there is no connection. So while fabricating it, we can fabricate it, but while making the connection, we will not make the connection that is a buried connection, metal layer contact. Okay. So if I draw its stick diagram, it will look like this. It's a very simple stick diagram to understand. So I'll explain this so that later on you can draw it on your own. So this is the gate connection, so which will be fabricated using polysilicon layer R2. So there will be another polysilicon layer, and on this there are two transistor on each polysilicon. So and both are N type. So what we have to do is we have to draw a diffusion layer of green color. So wherever the green color diffusion layer crosses the polysilicon, there is a transistor. So this is first transistor, and here you can see this is third transistor, that is this one. So this is first transistor, this is second one, this is third, and this is fourth transistor. So here we are first transistor, this is third transistor. Now we are going to fabricate this. So here there will be a straight line, so it will fabricate this third transistor and the second transistor, and then for this we will have this one, fourth, which here the diffusion layer crosses the polysilicon. So this is fourth transistor. right? Now, after fabricating this, after having this diffusion layer, we have to think about the connections. Now here you can see all the diffusion layers are connected together and they are connected to ground. So here what we have done is we have extended this and we have extended the diffusion layer and it is connected to ground. Now once it is done, so the source connection is done and we have to take care of the drain connections now. Here there is no drain connection, so you won't find any connection here. But here there is a drain connection, so you can see a buried contact between the uh, metal and the column. Okay, one more thing. These beat lines are fabricated using metal lines or metal C1 and C2. Okay, and wherever there's a drain connection or wherever you want to store zero, the drain a buried contact is created. So like this buried contact is created here. Okay, so this gives you a stick diagram. Now once you have the stick diagram, you can draw uh, a layout, mask layout for this ROM structure. So I have shown you the uh, stick diagram. I hope you can draw the mask layout using lambda rules here. Okay, so that's about the mask layout. Now it can be extended further for 4x4 ROM, 4x4 ROM, NOR ROM. So this is the same example that we have seen in the first slide. If you remember, this is the same example. So let's try to draw a layout for this. Of course, now you know how to draw the stick diagram. So this is the exercise question. So you have to, this is question number 1. So here you have to draw the stick diagram, and then from the stick diagram you have to draw the layout. So it's very obvious looking at this. Let's consider any row for that matter. Let's assume R4. Now in R4 you can see this is nothing but the polysilicon layer. These are diffusion layers 1, 2, 3, 4, where they are where there is a cross of diffusion layer over the polysilicon. There is a transistor form. Now here, because this is the 4 transistor, the drains are here. This is drain, this is drain, this is drain, this is drain of this R4. The sources, this is source, this is source, this is source, this is source. This source is sharing source of R3. So this part is source of, these are sources of R3, and these are sources of, when they are shorted together and they from their common connection there is another diffusion layer which ultimately connects to the ground. And here first we need to store 0, so that means the drain should be connected to the beat line. So there is a metal beat line over here where the drain is connected. Here it is open, here it is open because 0, 1, 1. So whenever you want to store 1, you keep it open. Whenever you want to store 0, connect the drain to the metal line. So like it is shown here. Okay, so it's very simple to draw. I hope you understood it, and you can draw it using a color rules. You can follow the color convention for this using the lambda rules. Of course, the area can be further reduced. The required area further can be reduced. There is one way of reducing the area. What we can do is, instead of having the metal at the same level, we can fabricate metal on the top of it. So because the metal distance has to be 3 lambda, this rule when we want to follow. So there won't be such rule because of course there will be rule, but then because it will on the top of this layer will be top of this, so you can still reduce the inter metal distance by fabricating it on the top of the diffusion layer. So this is one way of reducing the area required. Another way is shown in the next diagram. So here what they have done, so here you can see this is R1, this is R2, this is the same problem that we have discussed. So here you can see the sources are sharing, they are connected together, of course, and it is connected to ground permanently. Okay, now that is done. So this is about R2. Now R2 has drain downward, so there is a drain, there is a drain, there is a drain, there is a drain of R2. So what we can do is R3 drains are always at the top and R2 drains are at the bottom. So we can share this diffusion. So this is drain of R3, This is drain of R3, this is drain of R3, this is drain of R3. So what we can do is the same diffusion layer or region can be used, can be shared for the drain. So if you look at this, what we can say, we talk about R2, then R2 shares diffusion area with R1 for sources, and R2 shares diffusion area for drain with R3. So for R1, it shares the source diffusion area. For R3, it shares the uh, drain diffusion area. So same can be discussed about R3, R4, and so on. So this is another way. Of course, this metal lines can be fabricated on the top of diffusion area to reduce it further. So with this, the area required can be shrink. So this is how the but in this case, one thing you have to notice here, that all the drains are connected to the metal lines. You can see there is no disconnected metal line. I mean, there is no disconnected drain. There are no disconnected active transistor over here. But if you want to store zero, how can you store it? So the technique used here is, instead of disconnecting it, because if you don't disconnect it, then you just see this is the same layout, same layer that you have. You just have to keep on repeating it, right? So it becomes very uniform, so which increases the density. There's another advantage of it. I'll discuss it later. But as of now, we can see there's a uniformity is one of the advantage. So uniformity. So it's very uniform, and the uniformity leads to the higher density. That's one advantage that we can say. Second advantage, I'll write later. Just remember that I'll just tell it later. Now, before that, let's see what exactly we do to store 0. Because for 0, there has to be connection. But for 1, there should not be a connection. But in this case, you can see, even if I want to store 0 over here, 1, 0, 1. So 0 is fine because the drain is connected to the metal column, that is metal connection, or the column line, beat line, and the source is connected to ground. That's fine. But in case of 1, we don't want anything, we don't want a transistor here, but because we have a uniform design of a cell, so we fabricate a transistor. So to get rid of this transistor, and the drain is connected to the beat line and source is connected to the ground, so we have to get rid of this transistor. So what is done is, once we fabricate this, one more mask layout is used, and uh, implant is added to the channel. So after the addition of channel implant, it is added in such a way that its threshold increases beyond VOH, or the maximum voltage, that is VDD. So its threshold is increased beyond VDD, because anyways the maximum voltage that can appear at this column is VDD, and at row is VDD. And if your threshold voltage of this transistor is greater than this, so even if it is activated, still the transistor will be turned off. And if the transistor is turned off, it is as good as not connected there. That means it is storing 1 at the location. And repeat, what we'll do if I want to store 1, so let's consider this R3. So if I want to store I'm supposed to store 1, 0, 0, 1. So while fabricating it, it will be fabricated uniformly. There will be drains connected, there will be source connected. But then what we can do is, we will add channel implant to this location and this location. So it is, the channel implants are added in such a way that its threshold voltage is greater than VDD. And what is the maximum voltage that come at the R3? Is logic 1, that is VDD. So these transistors are never going to turn on. So these will be always off. And if they are always off, they are as good as not connected there. That means when this is activated, this column will never find path to the ground. So it is not there. It is also not there. So as good as storing 1 over here. Okay. So that's one advantage of this. So one advantage I told you is uniformity. So the connection is very uniform, the fabrication is very uniform. This adds density, it simplifies the fabrication process. The biggest disadvantage I want to tell you about this is, suppose I want to I have a foundry and I want to fabricate various types of ROM. So a client would give me what kind of output or what kind of data it wants to store in the memory. So it can have several bits like this. So suppose this is the output and it is just 4-bit, but it can be 64-bit or of any size. So in that case, what I can do is I will just have a simple layout structure, let's say 64 by 64-bit size. And suppose so this will be a standard NOR ROM I will have. Okay, so once I have this, so for this NOR ROM I will have a unique or a standard mask for it. So there will be a uniform mask for it. So uniform mask. So suppose if a client asks me for two such ROMs, one with containing one type of data, that is data one, another is data two. So for data one, suppose in data one is nothing but a combination of these rows. So what I will do is based on whenever it is zero, so I'll use one standard ROM chip and I'll just or mask set, and I'll add implant to the location wherever I want to set one. Now, when I want to set another set of data, D2, what I'll do is I'll take another set of standard ROM structure or ROM array, and I'll just add one more mask, which will uh, which will which will store data based on these ones, and wherever one I have to store, I will just implant those transistors. So what I can do is here by doing this, my fabrication process is becomes a lot simpler, because if I have such kind of connection, then every time I have to design another ROM mask layout. But if I have this kind of structure, I don't have to design every time, because this is the standard layout that I have. Now just I have to decide where to implant this doping, and here that option is not there, because yeah, of course, here that option is not there because I have to make sure that there is a drain connection, there is drain connection. So the layout will change as this data changes, the layout will completely change. But the advantage of this type of architecture, whatever your data is, it is 0101. So let's say it becomes 1110. So what I have to do, the layout will remain same. I have to just take care of the implant. So there will be implant here. So I have to just make sure the implant is there. And for the implant, I'll use one more mask. That's it. Otherwise, rest of the mask will remain same. So that's the biggest advantage of this type of fabrication. So I hope you have understood this. So you can draw a stick diagram for this. This is second question, second exercise for this, and you can use electric software to do this, solve both the questions. Okay, so this is how a layout would look like. So this is a standard layout. Just I have to make sure that wherever I have to make zero, I will have to add implant over there. So yeah. So this is about the NOR based ROM. I hope you understood it. So let's quickly go through it. So we have seen whenever the data is stored, it is stored in the form of NMOS connection, and here the NMOSes in a column are connected in parallel. That's why it's called as NOR ROM. And uh, then we saw, but there it faces three limitations or three disadvantages. One is static power consumption is more. Second is the area requirement is more. Um, and the third is probably the uniformity is not here. So this can be avoided by using a dynamic ROM. So static power consumption reduces further, and then the density can be increased by using various arrangements. So one arrangement is having the common source for the consecutive rows. Then it can be further. Then we have seen the layout. Then it can be further increased. The density can be further increased by sharing the drain of the consecutive or the consecutive column or consecutive rows. So we have seen this type of connection. So that's about the NOR based ROM. So we'll stop here. I hope you understood this. So we'll continue with this ROM in the next lecture. Thank you.